moving on with the theory, here's our next result, proposition 139. And this is about a context where you have an algebra of sets, not necessarily a sigma algebra, and an additive function, so not necessarily countably additive. But it gives you under this condition, it tells you, this is the main thing to focus on, it tells you about sort of a different way of looking at countable additivity. It gives you an equivalent condition, or another criterion, which is something we call countable subadditivity. So remember, countably additive, mu is countably additive, means if you take any countable collection of disjoint sets that are in the algebra of sets, whose union is also in the algebra of sets, then mu of the countable union equals the sum or the infinite series of the mu's. Countable subadditivity, this thing that I'm describing here, is the property that if you take any, not necessarily disjoint, collection of A sub n's that are in the algebra of sets, whose union is in the algebra of sets, then even if they're not disjoint, you at least get this inequality. So mu of the union is at least less than or equal to the sum of the mu's. Now, if you're thinking about measuring areas, like literally measuring area using your measure or volume or whatever, then this is a pretty plausible thing to have, right? If the ANs are not necessarily disjoint, then the sum of the mu's might double count and give you an overestimate of what the area actually is, because of the intersections between the sets being counted multiple times in the sum. Okay, so that's why you would just expect an inequality like this. But it's definitely pretty clear that this at least implies that this is implied by countable additivity, right? So this is like a weaker looking condition that is still enough for countable additivity, which makes it very convenient. That's the convenience of this proposition. It's like, hey, are you in a context where you have an algebra of sets and an already known additive function, and you want to prove it's countably additive? Well, then you only need to prove this condition, which is countable subadditivity. And that would be enough. Okay, well, I'm sort of introducing the whole thing by focusing on the important part and the most involved to prove part, although it's not super crazy or anything. But here are the other parts. So same context, algebra of sets, additive function, then this will be super easy to prove, but nice to have stated in a proposition, right? So you don't have to prove it every time you want to use it. If you have an inclusion, then the inclusion becomes a reasonable inequality when you apply mu. And if you have a, this is basically the finite sets version of the countable subadditivity. So you can call this just finite subadditivity. If you have a collection of things in there and not necessarily disjoint, then mu of the union is less than or equal to the sum of the mu's. So inequality here. And these not necessarily disjoint. Remember, what we have from additivity is when these are disjoint, then we get this. Notice that in this proposition, when we talk about finite additivity, when we talk about finite subadditivity, we never need to talk about whether or not this is in the algebra of sets. That's because it's an algebra of sets. It's automatic that when these are in, that the finite union is in. It's closed under finite unions. On the other hand, we do not know that it's closed under countable unions. So when we talk about these being in the algebra of sets, we also include the condition that the union is in the algebra of sets, because that might not be automatic. Okay, let's do this really easy one first. So this is part one, the one about inclusion becoming inequality. So here's our global assumptions, algebra of sets, and non-negative additive function. Remember, it's supposed to be non-negative. That's up here. We actually will need that here. So suppose you have two things in the algebra of sets, A and B, and you have this inclusion A subset B. Then here's a way to look at it. Rewrite B as actually B remove A union A, like this. Now, first of all, B is equal to B remove A union A. This is because A is a subset of B, so normally you would always have this inclusion, but we also have this inclusion just for these sets because A is a subset of B. So this is a way of rewriting B, and since fancy A is an algebra of sets, when you take a complement like this, that's also in fancy A. And these are clearly disjoint. They're in fancy A, and mu is additive. So we have this. Pretty sure we've made this kind of argument before, but I think it was in a different context. Hopefully this is the last time we make it. I think this will be a context that we're in a lot. So yeah, now mu B is greater than or equal to mu A, because mu B is mu A plus something, right? Plus something non-negative. So you see, this is where we need this to take non-negative values. If your mu is allowed to take negative values, this argument does not work. So this is since all right. Let's now work on part two. Finite additivity implies finite subadditivity. Okay, let A be an algebra of sets on X, mu an additive non-negative function, and A1 through AN in fancy A. Then let's just point out it's automatic that the union is in there. So we're actually going to focus on two at a time. So let's think about mu of A1 union A2 to begin with. So right now I cannot apply additivity to this setup because these are not disjoint, right? But I can rewrite this as A1 delete A2 and then union A2, right? A1 union A2 is the same as A1 delete A2 union A2. Now these two are disjoint and they're in the algebra of sets, since algebra of sets closed under complements. So I get this equality from additivity. And now from part one, since this is a subset of A1, this is my inequality that I proved in part one. And there's the two-set version of what I'm trying to prove. Right now I just need to extend this to n sets. So this all works for n equals 2. Now, what if I take a union of these n things? So look at that union of n things as actually a union of n minus 1 things, and then the nth one. And I can group the union however I want, so I can view it as the union of these, then union that. Then according to my result about the union of two things in A, in fancy A, this should be less than or equal to mu of the first part plus mu of the second part. And you see how this will power an induction step? We can reduce the n case of this theorem to the n minus 1 case, right? So if you had proven the n minus 1 case, then you could go ahead and do another inequality and cut this one down, right? And you'd get what you want. So let me just end here and say we can finish by induction from here. It's kind of interesting that sometimes instead of actually doing the induction, we just say that it can now be done, right? That's because we're all so familiar with induction. So this often happens in math when there's a technique that everyone who's expected to be reading the proof is familiar with, then you never actually apply the technique anymore. You just say, now do this technique. I think this is one reason that it's sometimes really difficult to read papers in a field that you have not really broken into, because they'll be using their sort of internal jargon. Oh, now just do this, and you'll finish the proof. And it's something that all the people in that field are really familiar with. Okay, here's part 3. So same context, A is an algebra of sets, mu is a non-negative, not countably additive, just plain additive function, and then we will prove that mu is countably additive if and only if mu is countably subadditive. So I think I might have said that this direction is trivial, but it's not exactly trivial to see that works. I do feel like this direction is the sort of strong thing to prove, since this to me feels like a weaker condition, but I'm not certain that I'm right about all those things. Anyway, this direction is not totally trivial. So say mu is countably additive, and suppose you have a sequence of sets, so a countable collection in the algebra of sets, and suppose this thing that's not automatic, which is that the union of these guys is also in the algebra of sets. Then define Bn, so we're going to define this family of sets Bn, so that they sort of take this running union. So B1 is A1, B2 is A2 unioned with the previous guys, B3 is A3 unioned also with the previous guys. Then the union of the Bn's is clearly going to be the same as the union of the An's, right? And the Bn's are nested, so each successive B is going to be containing the previous ones, because it is the previous ones unioned with one more thing. So then the Bn's build up to the same set that the union of the An's is. So the purpose of these Bn's is to get us into this context. We wouldn't be able to say this about An's, right? I couldn't put An here because they're not nested. They're not necessarily nested. And by the way, the Bn's are in fancy A. That's because fancy A is an algebra of sets, and the Bn's are all finite unions taking place in that algebra. So we had a proposition last time that told us about 3 equivalent conditions to mu being countably additive. And one of them was called mu is continuous from below, quote, continuous from below. And what that means is when you have a bunch of sets like this building up to another set, and all the sets involved are in fancy A, then the mu's limit to where they should limit to. So this is sort of a continuity statement, right? This is like a quote, limiting statement for sets, right? The Bn's approach this, then the mu of the Bn's approach the mu of this. Looks like you're saying mu is continuous in some way. So this is by proposition 133. And just to remind you, proposition 1 through 3 was about this exact same context, where you have an algebra of sets and an additive function. I think we didn't require it to be non-negative, but we had an algebra of sets and an additive function. And then we said countably additive if and only if continuous from below. Now, we already know something about the mu of the bn's, thanks to the previous part. So if I take mu of bn, then that's mu of the union of the an's. So this is fix any particular n. Then it's mu of this finite union, right? And mu is additive, and we already proved that in this proof of part 2, we already proved that for an additive, let me show the full thing here. For an additive function, it is finitely subadditive, right? So we already proved this. So I'm going to use this inequality. That here, this is going to be less than or equal to this sum. Okay, but look at this sum. This is a partial sum in a certain series, right? So this is the nth partial sum in the series, which may or may not converge as far as we know right now. This is the nth partial sum in the series, which is the sum of the mu of the an's. So this is the nth partial sum in that series. Now, for that series to converge, the sum of the mu an's is for this sequence of partial sums to converge. And it does, because it's this sequence of numbers, right? And it converges to there. Sorry. No, it's not equal to it. It's bounded below by it. That's actually throwing me off there. So I don't see how we know that that series converges at all. But at least we have an inequality. So let me conclude what I can conclude here. If the series of mu an's converges, then what does it converge to? It converges to the limit of this sequence of partial sums, right? And the terms of this sequence are greater than or equal to the terms of this sequence. Now we can apply the order limit theorem. So by the order limit theorem, so basically take the inequality you see here, this less than or equal to this, and that's what we're applying the order limit theorem to. So take n goes to infinity in that inequality. Then this goes to apparently mu of the union, and this goes to whatever this series is converging to, which we denote by the symbol for the series itself. And it's an inequality. So the inequality is preserved under the order limit theorem. Okay, so that's good, but that required me to assume that the series converges in the first place. So I'm a little bit puzzled as to why the theorem statement is like this. It doesn't seem to contain anything that requires this series to converge. And I just took this from the book. Okay, here's actually a really trivial way to break this. Take any measure space and take any single set A that has positive measure, strictly positive measure. Then for your collection of countable family of sets in A, just take that one set repeated over and over again. Then the union of that one set over and over again with itself is just that set. So mu of that will be some positive finite number, right? But then this sum will be a sum of the same constant repeated over and over again, a positive constant. This will not converge. So just to give an explicit example, let's say x is the natural numbers, this is our sigma algebra. It's definitely an algebra because it's even a sigma algebra. It's all things, right? And then for mu, let's take the Dirac delta measure at 0. So it gives 1 for any set that contains 0 as an element, and then it gives, actually, 0 is not in the natural numbers in this course, right? How about 1? It gives 1 for any set that contains the natural number 1, and otherwise it gives 0. Then let an be the same set for all n. Or if you want, you can make them different sets, just different sets that all include 1. So maybe well, I don't know, make them all this, right? Make them all this. Then the union of the ANs is this. So mu of the union of the ANs is 1. On the other hand, the series diverges, right? It's a sum of 1s. Okay, so here's what I think is going on here. I think you're supposed to interpret this series as taking the value infinity. And I'm putting it in scare quotes because we haven't really discussed the extended real number line in this course. And I sort of only want to introduce it at the moment that we start using it a lot, if that moment comes. I don't want to introduce it and all the rules for that, and then just use it for one stupid little thing. But it seems it's coming in here. I think what's meant by this inequality is that if the series is that when the series diverges, then we consider it to be taking the value infinity, and then this inequality still holds with the infinity on the right-hand side, because we allow ourselves to interpret those inequalities in a certain way. So maybe I will add a note here. So just note that the series on the right-hand side is allowed to take the value infinity. Or, you know what? I think I have a better way to do this. Since whatever inequality we're interpreting here is going to be trivial when the right-hand side is infinity, yes, in the extended real number line, you will find to no surprise that every real number is less than or equal to infinity. That case is trivial, so how about we just leave it out of here so that we don't have to even talk about it. I think leaving it out will make this proposition no weaker, really. So we're countable subadditivity is this inequality whenever an is a sequence in there, with the union in there, and with this series converging. Okay, so I think that now I have proven the one direction of part 3, now that I've modified it to include this yellow comment. Now I get to say, yeah, we only care about the situation where this does converge. So if this does not converge, then it's a series of positive numbers, right, or non-negative numbers. So the sequence of partial sums will be an increasing sequence. When you have an increasing sequence not converging, you can say it converges to infinity. And there is a formal meaning we can associate with this idea of converging to infinity. So that would be fine, but just no reason to bring it in right now. All right, so that's one direction. Countably additive implies countably subadditive. This is the one that I said was trivial. I guess it's not that trivial. I mean, it is trivial, but you shouldn't say something is trivial and then talk about it for like more than 10 minutes, right? Okay, so assume countably subadditive, and now we're going to prove countably additive. Okay, so for proving countably additive, I should let an be a sequence in there with the an being pairwise disjoint, and fancy A here is not necessarily a sigma algebra, right? So I have to say and the union of them, which for convenience, let's call that A, is actually in there. I think now I'm running into that same problem again with the series possibly not converging. So at this point, I want to prove, the goal becomes to prove that the mu of the union is the sum of the mu's, right? And included in that assertion is that the series converges. But I have now modified countable subadditivity to only tell me something about the situations where the series converges. So it doesn't not tell me that the series converges. Oh, but you know, I might be able to get an upper bound. I think using this, I'm actually going to get an upper bound on the partial sums. So maybe I can prove the series converges. Okay, maybe there's no problem. Let me just go ahead and see what we can do here. Okay, so let me start with this kind of union up to the nth one. Now, we already are assuming that mu is additive, right? So this is actually equal to this finite sum, right? So this is all under the assumption that mu is known to be additive. Then we're showing that countably subadditive implies countably additive. So we have this, and we also have this inequality from part 2 over here. Or sorry, from part 1. If sets are included in a set, then their mu is bounded above by the mu of the larger set. So since anytime you union a bunch of these, that's a subset of the union of all of them. This is less than or equal to mu of everything. So now I'm sort of getting this upper bound by taking advantage of the fact that I have assumed that when I union all of them, that that's in fancy A, right? That's an assumption I made here, and that I got to make. That's part of the proposition, that the union is in fancy A. Okay, so you see the partial sums are bounded above. So then the sequence of partial sums, these partial sums, is an increasing sequence. These are all non-negative, right? I'm assuming that mu takes non-negative values. So this is an increasing sequence, and it's bounded above. So by the monotone convergence theorem, it does converge. So from here, by the monotone convergence theorem, now we know this series converges. So here again, we're using this fact that that we're looking at a non-negative function mu. Now, now that we know the series converges, now we can apply the countable subadditivity. So we have assumed mu is countably subadditive, right? That means if the series converges, which we now know it does, and if all of these conditions hold, which they do, then mu of the union is bounded above by the sum of the mu's. So let's see. We have this less than or equal to mu of the union. So I'm just rewriting the inequality I've already written down up there. By the way, this is all for each n, we have the following stuff. This is bounded above by mu of the union. So this is rewriting what I wrote up there. And then here's countable subadditivity. It's that this is less than or equal to the sum of the mu's. So this is by the assumption countable subadditivity. Okay, now look over here at this being less than or equal to this. So this is one fixed real number, right? And then I've got this is less than or equal to that number for all n. This is our sequence of partial sums for this series, right? So now apply the order limit theorem to this inequality underlined in blue. We get that the limit of this sequence, which is a sequence of partial sums, so its limit is this series, I'm sorry, actually, you have probably noticed that that would give us nothing, right? It gives us that the series is less than or equal to itself. What I really want to look at is this. Apply the order limit theorem to this portion, and this will come in a moment. Then we get that the limit of the left-hand side is less than or equal to, so here's the limit of the left-hand side, that's less than or equal to that one fixed number on the right-hand side. And from the countable subadditivity, we have the other inequality, right? So this is what came from the order limit theorem. This is what came from countable subadditivity. And to be honest, I didn't really need to mention the countable subadditivity up here. This did nothing. And that's it. So that proves an equality, right? Both inequalities. That is the equality that's needed for countable additivity. Okay, so we had a few hiccups there, but I think it worked out once we added this. So summary, if you're in a context where you know your mu is additive and you've got an algebra of sets and you know you have additivity, then to go from additivity and get countable additivity, it's sufficient to just have countable subadditivity, where unless you want to go and figure out how the extended real number line should work and define the idea of converging to infinity and things like that, unless you want to go do that stuff, this is a perfectly good definition, I think, for countable subadditivity, to say that it tells you about those situations where this series does converge. And now that I point to it, I'm seeing a typo. It does not make sense to add up sets, right? This is the mu of the ANs. Okay, so that's that.